Thank you very much for coming this afternoon. I understand that I'm standing between you and the happy hour at 5 o'clock, so hopefully it's going to be a pleasant journey. My name is Mahmoud Al-Daccak. I'm the CTO and EVP Product Development at Haivision, and I'm happy to share with you some of our thoughts and journey as we went through this SRT technology and then open sourcing it. So just a rough outline of what we have. I'm going to just go over a quick overview of what we have. Try to cover some of the details of the protocol, not extremely too much in the weeds, but enough maybe for you to get a flavor of that. Talk a little bit about some development updates and what we're doing or what's cooking. Maybe refer to some real life implementations, and then see how we can get all engaged in this effort. We've started this effort a while back. It's all about enabling low latency video contribution distribution, so I'll make those more clear as I go in the presentation. But this is not really meant for delivery to the end consumer or end viewer. It's for contribution and distribution mainly. And it also supports fast file transfer, which is not very commonly known by people, but it does support fast file transfer, and you'll see more and more products actually using it in that area. It covers on few aspects there. Tries to get your quality to the best possible under different conditions in the network, whether it's network jitter or dropped packets or delays on the network and whatnot. It caters to the low latency. Low latency in the sub 1 second area. And it's tunable, so you can set your latency based on either your network condition or what you desire to get out of the signal. Very important, being firewall friendly. When you have an event somewhere and you want just to send back that event to the headquarters or something, you don't want to wrestle with firewalls and all that. So it's very important. Secure, and finally, open source. So if I just walk through a little bit of history about in that aspects. So we started like any good things. We started on a piece of napkin. Actually, it's a piece of cardboard there, and that's actually the piece of actual cardboard that we had. In 2013, towards the end of 2013, we showed the first demo at IBC, and it was HEVC with SRT from a hotel room to the show floor. And it proved successful, and people liked it. We shipped our first product on it somewhere in 2014, I think around NAB. We added some firewall friendliness there. Decided to open source it at NAB 2017. We didn't expect, how much the market and the industry is thirsty for something like that, to actually be able to deliver your video free of network impairment over public internet or unmanaged networks. So we open sourced it, and the rest is almost history from there. We released a 1.3, which introduced some multiplexing capability on the same UDP port, and then some bidirectional. I'll talk about them there. So right now you have almost over 50 products that are SRT ready, which is great. It's been only 18 months since we open sourced it. And in the SRT Alliance right now, we have more than 170 members already. A lot of them are active, a lot of them are contributing. And there's a lot of companies also that we don't know about. I mean, you walk the show floor at NAB or at IBC or other shows like this, and you'll find people implementing it, but we don't know about them. And that's the beauty of what we wanted to do, get something to the people that use it. It's simple to implement, and get the benefit out of that. So the challenge that we try to overcome is very simple. You might have an event or a source somewhere. You want to send it to a destination. A decoder or a data center or whatnot, and you're going to traverse the public internet and with all the impairments of that public internet. So the mission is very, very simple. Get it from A to B without jeopardizing the video quality and without adding a lot of latency in that. So the things that we try to solve for, correct for any packet loss, jitter, the delay, and also adjust to some bandwidth fluctuation. So here you have like some examples of actual examples that we've done with some of our tests. This is like the initial source with live source, initial source with 2% packet loss, and then HEVC and H.264, basically 6 megabit, 4 megabit and 6 megabit. And you can see also that the latency is very, very well under control. So I'm going to dive a little bit more on the different kind of use cases or focus area market segments that we focus on, and then try to take it a little bit more on the technical side. So just to re-emphasize what I was saying of where we see SRT being deployed, and we see it in both areas. The first of them is the contribution. So the contribution can take different flavors. You're either doing field contribution for news and sports in events, for example. Return feeds, for those who are not too familiar with that broadcast term, is basically your return feed. If you have a talent, for example, in the field, usually their signal is going to the station, and then that feed comes back so that they can see themselves. And it's very, very important, plus it gets monitored. So it's very important to get the return feeds for the confidence of the talent, confidence monitoring, of course, live interviews, and last but not least, remote production. Remote production's always been out there. It's possible. It has a lot of advantages to save on the cost of labor and all that when you send them on site. But over the public internet, that's what we're trying to enable more and more, and that's what people are looking for. So basically from a venue, you want to traverse the public internet, you want to receive these cameras somehow at your production, to your production switch, and make sure that they are frame accurate. So over SRT, you're able to have that contribution from different encoders sent to a bunch of decoders. They all will be frame synchronized and then outputted to the production switch, for actual production. And then, of course, you have the return feed. So SRT is extremely crucial for such an application, and it's leveraged a lot there. On the distribution side, that's basically when you're taking those feeds either from a TV station or an area where you have these signals, and you send it, basically could be into a data center, for example, where then you ABR it and send it over the top. So that's the distribution part. So it's not going to the end consumer. It's actually from your production studio or from your TV station or from whatever these signals are originating, and then they get sent to the data center or the telcos, where they get transcoded possibly into an ABR and then sent over the top. So really the main applications there, or the segment, is the live linear OTT. A lot of people are familiar with MVPD. So there's a huge shift to virtual MVPD, and that's what's helping in there. And of course, for international syndication and whatnot. So these are the two areas that we focus on. And it will come clear why we focus on these specific areas and how we can leverage those specific areas. So when we started off, we had some design targets that we wanted to cover with this protocol. And we wanted, of course, to cover video. We want audio, metadata. That's very obvious. But then, control data, which is really real-time data that's sequenced that you need to guarantee it. So it's control data or any type of data. So we built this so that it's not aware or dependent on any format. So it is content agnostic. So whether you're sending video or you're sending control data that you needed in a certain sequence, it doesn't matter to the protocol. The protocol doesn't cater to video specifically. It caters to real-time information sequenced. So it's a content agnostic. We wanted it to be format agnostic, obviously, protect the stream integrity, of course, the data integrity, being secure. We wanted it to cater to live streaming, file transfer, so not only just live streaming, it's also file transfer, of course, real-time or non-real-time. IT friendly, because you'll encounter a lot of these hurdles as you try to traverse different firewalls, and sometimes you have cascading firewalls. It works at the transport layer, so it's really at the packet layer, so it's not really aware of any higher level like audio or video. Could be multiplexed, bidirectional, so you can send information one way, get the information back, so you can be sending audio video one way with audio talkback if you want, or control data, for example, camera PTZ back to the stadium or the event or whatnot. And the latency, we always targeted sub 1 second. We achieve a lot better than that. It's dependent on your network condition and the RTT, and then that latency can be tuned. So this is a diagram borrowed from our friend at Wowza, which we collaborate with a lot. I wanted to kind of clarify things, because latency is like beauty in the eye of beholder. Some people, when they say low latency, they talk about 2 to 3 seconds. Some people, when they talk low latency, they talk about sub-frame latency, line latency latency. So in a production suite, though, some people talk about sub-frame latency. So the latency we're talking about here is to really guarantee some kind of a near real-time. So if you have a second screen experience or a bidirectional, like interactive or whatnot, that's what we're talking about. And that's the area where we play with. So SRT is unicast. It's really leveraging, it's running over UDP with leveraging ARQ, which is automatic retransmission request. And with that, we have a lot of tuning into the protocol so that we do fast retransmissions. So there's a lot of optimization on how we do the retransmission. We have selective retransmission. Sometimes it's like too late to get that packet, forget it. Like TCP, make sure that every packet gets there, and you get acknowledged for that, but then you might be waiting. UDP, just dumping all these packets and hope they arrive. ARQ, try to say, hey, this packet didn't arrive, please send it back to me. But sometimes the network is so bad that it's like a self-fulfilling prophecy. Things starts to kind of snowball. You don't receive the packet, you ask for it, you try to send it, it gets lost, you ask for it again. So you need to figure out how you can do some of the fast retransmissions, at the same time be selective. For example, if the time has passed for a certain frame, why are you trying to recover its packets? It's gone. You've seen it or not, it's gone. It's so there's some kind of glitch. There is no reason to kind of backlog everything. It is FEC compatible, and I'll talk a little bit more about FEC. It's really something that you can implement and hook up to that SRT, so that instead of ARQ, you move over FEC. And that will be important for unidirectional or multicast support. Again, for example, there are certain links that are unidirectional only. Satellite links are unidirectional only, so you might want to have that. As I said, it does not focus on the consumer delivery. Our objective is to scale to the thousands. Of course, when you go to HLS and Dash, it scales to the millions. That's not what we're targeting. We're targeting a much lower scale. So we're on this side of the fence as opposed to that side. At the same time, as you increase, you try to reduce your latency, your scalability goes down, but we're trying to maintain it in the thousands. So that's, and again, there's the sweet spot for what is right now talked about in the OTT. Initially, OTT, no one cared about latency. Now, a lot of people actually do care about latency because of that second screen experience where you're getting your social feed on one screen and you're getting your football match on the other screen. And if you have a lot of latency, like 45 seconds of latency, that could be a problem. It can spoil the score or the goal or whatever. So it's good to understand which problem we're trying to solve. And when we looked at, we tried to ride the transport stream is almost the analog to SDI for those of you who know SDI. So it's a trusted, well-established that everybody uses it, and that's what we wanted. We wanted to carry signals over that. Of course, we're not specifically dependent on that, but that's what we do, IPTS over WAN. And this is designed to run on any platform, really. We run it on the very, very underpowered platform and on server-grade platform. So it's designed to do that. There's a lot of concepts here. Some of them, like SRT fits into or leverages. Some of them, SRT is trying to provide an alternative. SRT is not trying to really replace anything. It's trying to present an alternative so that you can get your job done if that's what you have as a need. So again, as I said, it relies on unicast, so it's a unicast only, although if you, instead of ARQ, if you use FEC, it can be in a multicast scenario. It relies on UDP as opposed to TCP, so you don't have, UDP doesn't have the reliability of TCP, but we try to compensate for that. Of course, there is a lot of also mechanisms to try to get UDP to be a little bit more reliable, things like the multipass TCP or QUIC. We're not leveraging those. These are efforts, fantastic efforts at the transport layer. They're trying to actually accommodate take some of the advantages of the UDP and the TCP and combine them together. And there's many like reliable UDP, etc. But these, again, they are at the very low level transport layer. We're trying to build a little bit more intelligence there. We are more of a real-time protocol, so we're not chunked. So we don't rely on HTTP, but it's there. We provide an alternative, like with the SRT, to RTMP. RTMP, of course, is one of the widely adopted streaming protocol for real-time low latency. It suffers from a lot of issues, aside from it's going to be kind of, the support of it will be dropped in 2020, I think. RTMP is not to be confused by Flash. I know it's like really associated with Flash. But RTMP is a great streaming protocol, but it needs to maintain a connection, and there's a lot of issues with the connection disconnection, and you lose a lot of efficiency if you're going over a long distance. RTMP is not really suited. If you want to send a signal from Australia to the US, try to send it from Sydney to New York over RTMP and see what you get. RTMP over long distance is a big problem. At the same time, RTMP does suffer from bandwidth utilization. So if you have a 10 megabit bandwidth and you're sending it over RTMP long distance, you will not be utilizing more than a fraction of that bandwidth. So basically, it's something you're paying for, but you're not leveraging. So that's what we're trying to accommodate here. WebRTC has a great implementations. Again, sometimes it's not very well suited for either scale or very high bit rate, but it has its place. And HLS-, of course, they are delivery. Right now, there are some people trying to also use them for contribution. Akamai, for example, is very active in that. There's the CMAP, for example, low latency dash, which is very, very promising. It's trying to hit a sweet spot. You can operate it at around, I don't know, maybe 7-8 seconds latency, and there's a mode around 2-3 second latency, which is great. So they are, like they're solving the problem for that, magical 5-second latency for cable TV. But still, I think for a contribution and distribution, I don't believe in chunk delivery. I believe in more of a real-time streaming signal. So I still feel or believe that SRT is a lot more suited for that contribution distribution. For delivery, of course, there is no question that an HLS or dash, especially with the CMAP, now that you don't have to duplicate your essence, your video essence, that becomes a very attractive solution for you. So SRT is all about the latency and the buffering and how we manage that. So this is just like a very simplistic way of looking at it. Basically, you have a buffer at both ends of the, on the sender and the receiver. The buffer on the sender needs to be large enough so that it can accommodate roughly what would cost you to do like maybe 2 to 3 times RTT. So it has to have enough so that if the receiver said, I did not receive something, they can, the sender can still have it. So it needs to maintain a minimum of buffer. That buffer is tunable, as I said, like some implementation of SRT or some use cases where they say, okay, I really don't care about like getting me the lowest latency possible. I don't want it to fluctuate. So you can fix, you say, okay, I want my latency to be at this, and then we fix the buffer. Or the buffer could be variable based on the RTT time so that I can adjust it. I can lower the latency if the RTT time is low. But as a rule of thumb, it's usually our latency is 2 to 3 times RTT, and that's how you can get something from Tokyo to London. Usually it's around 400 millisecond, which is great. The way we do the NACs is also selective. So if there's a sequence of packets that was not really received, we don't send a NAC for each one of them. We know that something wasn't received and it's for a series. So we try to be less chatty on that channel back, which is very important. We have like a lot of adopters of SRT that are using it for audio only. And of course, audio as compared to the video is a lot less bits. So sometimes the metadata or the signaling becomes more than the actual data. So that's why we're very selective on what do we send over the wire in terms of control data for that protocol to make sure that we can cater to things like audio or control data without flooding the network there. So these are like the basics in terms of just the buffering. And of course, like you need to buffer a little bit on the receiving device. That is because you need to actually make sure when you give the packets, you give them in the right sequence. So this is more important with this slide. This is the problem we're trying to solve. You have an encoder that's producing something. Of course, the bit rates will go up and down based on the scene that's trying to encode for sure. If you have, like, you can get a CBR. So imagine this is a VPR, and it has a certain time signature. It goes over the internet, and you will lose packets and whatnot. But that's not the only thing that happens. The timing of these packets changes drastically, like it could vary. And that variation is really very harmful to the decoder itself. And for that case, you need to buffer a lot in order to kind of paste it and give it to the decoder. So what we try to do with SRT is not only recover for the packets and make sure we deliver to them, but also we do the timing. So basically, we timestamp all the packets, make sure that we deliver to you in the right order at the right time. So the objective of the whole protocol is to take the signature of the signal at the origination, at the encoding, and then try to reproduce it as close as possible so that you can give it to the decoder. So that's really the essence of the whole protocol, not only the packet recovery, but the retiming and make sure that you give these packets in the right sequence at the right time. And that is what, a lot of people, who tried that protocol really rely on in terms of, okay, well, I just set it, forget it, and it works. It's just because of that, how we keep the signature of the signal coming out. The packet structure, we recently published our documentation for there. I said it's really writing, it's dependent on UDP. So it's a very simple packet structure. You can have a 0 or 1 to say, is this a data packet or it's a control packet? And then you have the payload. So nothing really esoteric there. There is room for expansion. People already started, on the open source community, start to, propose certain things. We maintain also compatibility across, different version of the protocol, etc. So it's fairly self-descriptive. From a control point of view, the structure is very, very similar. Of course, the control information field is variable in that case, but the packet has a very similar structure, and also you have the timestamp for those control signals. So really, for a lot of people, they really don't care what is the control packet and what is the actual data packet. But a lot of people who are trying to customize or try to do something different, they need to know that. And they've been asking us to publish what we have under the hood. So we've done it recently, and you know, I think that's useful for a lot of people. I did mention a little bit about security, and I want to just pause a little bit here and talk more about it. So, of course, we can protect against denier of service attacks and whatnot, so that's very key. When you establish a connection, you don't want everybody calling you on that connection, and you don't know them, and then you can bring down your server or your device or whatnot. So that's a given. Of course, AES is also a given. We use Aes Counter Mode, and this is kind of key. Counter mode is actually the same mode used for HDCP protection in 2.0. It might be anecdotal to know that as a company, we managed to be an authorized retransmission technology for HDCP. Back in 2010, we got authorization from all content owners to actually transmit HDCP protected content over IP networks to 126 nodes. That was back in 2010. Only recently with the HDCP 2.0, they started moving things over IP and up to 16 nodes. What's important here is the same schema and protection that allowed us to get the permission from the TCP community and the content owners to move their HDCP protected content over IP networks is what is used in the SRT to protect it. So it's a very, very secure way of transmitting that stream, and that's one of the very pivotal point to a lot of broadcasters moving their signals with SRT, having that HDCP history in the background. The rest is like you do the encryption on the transmission. Basically, we encrypt at the TS packet level, so the payload with the TS. Usually, every 7 packets, we encrypt them. The AEC counter mode is basically just for short-lived keys that can alternate and change. And then, on the reception, you of course, decrypt and play them back. What's important here, we don't do key management. So you give it a passphrase on one end and a passphrase on the other end, and that's it. So we don't have a system. That's a higher level, application level, if you want to have that key management. What we handle is at the protocol level, we make sure that your signal is encrypted and safe. One key thing about this exchange is that we need to work in bidirectional. And it's very, very tricky to get it to work in bidirectional because you don't know who has the public and who has the private key. Is it the, this end or that end? It had to work in bidirectional. So that's also something that is implemented in the protocol. Another area is, of course, the data flow. And it's important, as I mentioned, that when you look at the data flow, the key thing is how can you be as friendly as possible to your IT department or customer's IT department. So in this case, you have a sender and receiver, and the content is going from A to B, obviously. The sender or the receiver, each one of them can act either as a caller or a listener. So it depends on which side of the fence you are on. So if you are, for example, the sender and you control the firewall there, then you can be the caller and the control is going there and then the content in the same direction. However, if actually the firewall and the rules of the firewall is more on the receiver side as opposed to the sender side, So actually the caller will, in this case, be on the receiver side, say, hey, I want to get that SRT stream. Then you're punching a hole out, and then you allow the content to come in. So really, it's important which side of the firewall do you control. Is it in location A or in location B? You only need to talk to one IT department to arrange this. Of course, this is like a very simplistic view of this in terms of the caller listener, but you can imagine that sometimes. Why do we have no signal? I apologize for that. Let's see if I can get it back. Is this still?
That's a good sign. No, you turn it off?
Sorry?
Is it off or?
No, it's not detecting any video from there, any connection from there. No. So now it's detecting. Okay, don't breathe on it. Okay, very nice way to do a break. So hopefully this will continue working. Let's pray. So as I was saying, so let's, as I mentioned, this is a very simplistic view. On the receiver side, you can be the caller, you initiate the call, and then you receive the content. You don't need to, it's a persistent connection, but what's important in that persistent connection is you're not paying. So let's say if you don't have a stream, there's nothing coming, you maintain the connection, and once you have a stream, you stay. And this is very, very important because otherwise RTMP is problematic in terms of initiating that connection. Let's say you have an event, and you have the camera rolling, and you're streaming back to your production studio or to your TV or whatever it is. Well, that's fantastic. You establish the connection, but maybe you need to establish the connection. The camera is loading, there's video, but you don't want to start sending that video and start paying for that bandwidth. But when the event starts, you don't want to scramble. So you can establish all your connections, set up all your routes, and then when the video starts flowing, it starts flowing. There's more details in terms of these firewalls also, in a sense that they could be cascaded firewalls, there could be multiple destination firewalls, so you need to keep all of that. So the sequence is fairly simple. You start with a handshake, you respond to the handshake, the sender kind of announce what capabilities it has and what it can do, whether it's what's the version, whether it's live or file, buffer size. You get a response, and then the flow goes. Again, very clear, very basic implementation. One of the things that you need to also be careful of is how you can pace your packets, and also not only just for the fast retransmission, but also for, how do you drop packets and when do you decide to drop packets, and then also what happens when you are losing packets. So sometimes when you're losing packets, it starts to be like, as I mentioned before, like a snowball effect. You lose packets, and because of you lose packet, you try to retransmit those packets. So now you're doubling your bits that's going out, but then you lose more packets, and then all of a sudden you get a network congestion and everything throttles down. And try to do that over bonded LTE, by the way. That's the worst thing you can do, is to send that and try to be, just be more aggressive, and you're not cognizant of what's happening. Then very, very quickly you get into a congested network and everything, grinds to a halt. So what we try to do is we provide a certain headroom, so that basically, because when you have a packet loss, you have more bits to retransmit. So it is, you have the bits that is coming from the encoder, of course, plus the retransmission. But at a certain point, you need to paste those. And at a certain point, you need to also either paste them or just drop them if say, like, time has passed, I don't have, I don't need it anymore. Thank you very much. Again, this is not a database transaction. TCP, again, it's suited to make sure that that packet gets there and is delivered. It's a transaction. Video or real-time data, sometimes it's not transaction, and sometimes you say, it's too late, I don't need it. Thank you. Of course, if it's a control data, that's different. So that's why you need to have, kind of more leverage and more control over what packets can be dropped and what packets cannot be dropped. So that's really, we covered the what is the packet structure. We covered what is the flow of the data. We covered the security aspects of things, and then we covered the timing and the packet pacing. These are the 4 core principles that are out there. Maybe moving from there, just talk a little bit about our roadmap. So we released 1.3.1 is just like a stability release, bug fixes and whatnot. And the 1.3 release, I think it was around NAB time, if I'm not mistaken. That's where we implemented the fully bidirectional support for both the transport and the encryption. So you can send data both ways. As I said, it's very important if you have either a talkback channel that you want to send back over the same connection, or if you have video going, audio video one way, audio video coming back, or you have the camera in one location and sending the signal and you want to control it through PTZ, for example. We added also the multiplexing. So right now, instead of having one UDP port per connection, imagine if you have 6 streams that you want to send. So you don't need to open 6 UDP ports and manage those 6 UDP ports. You can actually multiplex them over the same port. So basically, you can send 6 streams over one SRT connection. And again, that's also to make your life a lot easier when it comes to dealing with IT and opening UDP ports and whatnot. And of course, we introduced the fast file transfer support in the 1.3. In 1.4, we will be adding like what we call socket group redundancy. So maybe just to clarify, what does that mean? That's basically just to add reliability and redundancy to the protocol. So it behaves or acts very similar to 2022-7. So basically, based on first come, first served packets. Imagine if you have 2 SRT connections redundant, they go out of the sender, they get to any receiver, the receiver just picks up the first packet that it receives and in that order. So really the receiver can be as dumb as possible. It's not seeing anything that it is like dual streams or quad streams or whatever. It's just like, all it knows is I need to get these packets in that order, and whatever packet gets in, I receive it. So this is not just to have, let's say, dual redundancy. You can be sending, let's say, 3 or 4 redundant, or a lot of people some people use it, they send bonded LTE, public internet, and possibly satellite. So you can send through 3 mediums, and the receiver doesn't really understand any of that. It will just take the packet that it needs in that order. So this way you can send over different mediums. You can add the reliability or the redundancy. At the same time, you can guarantee the lowest latency possible. For example, if you set 2 routes, the internet over time changes over the day. So, certain routes get congested or whatever. So if you're routing something through Hamburg and you have another signal routed through, I don't know, Virginia, sometimes, it changes if you have a 24/7 kind of signal coming. And without having to adjust anything, because it's based on first come, first serve, you will always be picking up the lowest latency route that gets you there. And of course, we're going to try to improve on the congestion control so that we have a much more also efficient file transfer there. We've released the documentation finally, and a lot of people have been asking for it. So, the documentation covered the protocol implementation, the data structure, and the data flow. We're working on an RFC, so that actually, put it in that format and possibly, submit it to one of the standard bodies. So, not only we're open sourcing, but also we'd like to submit to a standard body to be determined, but first step is to write that RFC. And in the progress, we're publishing an API, so if you want to implement FEC, you can hook up your FEC and replace ARQ, for example, and then we're doing some kind of automated components for functional testing. So the main thing that is happening right now in progress is to publish that API. But we have a lot of things that are also either cooking or on people's mind of what they need to implement. We've been asked a lot for multi-link bonding. This is something that a lot of people are asking for, so that basically you can bond multiple links. So instead of the redundancy I talked about, is actually now you have multiple links and you just send the signal over the aggregate of those. Adding FEC, as I said, for unidirectional links like satellites, or to enable multicast if that's what you want. I don't believe in FEC being this the lowest latency. Actually, anybody who's checking FEC latency and the overhead of it versus ARQ within the SRT, they will be very pleasantly surprised that our latency is very, very comparable to FEC. So the FEC, I see it for unidirectional links and to enable multicast. A lot of people also ask for a slider. Latency plays with quality. You can increase the quality, but that will be at the expense of latency and vice versa. So we wanted a very simple tunable parameter for that. People also ask for stream prioritization, so please make sure that stream A has priority over stream B. The same thing for packet prioritization. I was talking about that earlier. Maybe you want to prioritize your audio packets or your video keyframes ahead of anything else, so make sure that you always service them. So if you don't want to use your keyframe, you don't want to use your audio, there will be glitches. It's very sensitive there, but your ear is not forgiving, so the protocol should be catering to that. Your eye is, believe it or not, is very forgiving. It might, if there is 1 or 2 frames that you miss, you will never see them. But if there is, few packets of audio dropped, you'll hear a pop immediately. So that's why packet prioritization is fairly important. And then adding some more support for the metadata so that we have out-of-band metadata. So there is a lot of work in that regard. Some of the work is also building what we call an Srt Hub. So you can imagine this is a big infinitely scalable gateway in the cloud, which is like a virtual video router, if you want to call it that way. Plug source A to destination B. So it's riding the backbone of Azure, and the beauty of that is everything is transparent to you. So you have a bunch of sources and a bunch of destinations. By the way, you have something called Srt Connector. So if your workflow happens to be just RTMP or TS, you feed it to that connector. It pairs with the hub. It becomes a source that you can map it to a certain destination to send it out. it's important to know that sometimes if you have an event in Australia and your data center for processing happens to be in US East because you don't have that processing in every data center, it's very important to get that event or that stream or that file from Australia to where your processing is. So that's how we handle it. So basically based on where you're originating from, you enter the Azure cloud from that region. So you enter it from Australian region, and then we say, okay, I'm going out somewhere in the US East, so I'm gonna go out in the US East, and I write the backbone of the Azure. Anybody who tried to write the backbone of Azure, they will notice that it's one of the best backbones there for the lowest latency possible. And writing it over SRT will definitely guarantee you the lowest latency as opposed to just traversing the general public internet. So this is something just leveraging a lot of the under the hood Azure components to really satisfy two use cases for live broadcast distribution. So basically you have an event somewhere and you want to send these signals back to the broadcast facility, and you don't want to start gateways or manually handle this. So you originate the signal in one place, it gets to the other place, and if they are in different geos or different or different regions or not, that will take care of it. And if your signal is a transport stream or RTMP or RTSP, you can feed it to the connector and then feeds it out. The counterpart of this is the distribution aspect. So in the distribution, you're in the origin service and you want to send it to your data centers for OTT distribution. So it's really the counterpart. But the main thing here is, again, your signal is in one place, where it needs to get to is another place, and how can you manage to get it there? Of course, you want to have the flexibility of defining, that virtual, video router in the cloud to enable that, so that you don't have to spin up instances. You don't need to worry about scale or anything like that. So this is really the Srt Hub is leveraging the Srt protocol to provide you with that type of functionality. Just to kind of try to close here, I thought of just finishing up with some of the real-life implementation and use cases. Most of them, they're just purely leveraging the Srt protocol. Some of them are, products, third-party products being used. Comcast, for example, is using Srt. Comcast, this is their footprint. They have different nodes across the internet where they have their major hubs and how they move their signals. So they'll be using it for live linear OTT contribution and distribution, leveraging all their presence over the US. So you don't need to follow all that complicated diagram, but suffice to say is basically you have the origination of the signal, you send it over SRT. So it's very similar to that Srt Hub that I showed you. It goes into the cloud, into the Comcast cloud, then over SRT. From there, it's fed to the edge, so it traverses the cloud, up to the edge. Again, leveraging SRT, and then it gets into the distribution centers. It gets to the distribution so that basically you can either ABR it or feed it to the likes of Hulu or whatnot, or process it in Amazon. So this is really a real-life scenario with Comcast for live linear OTT contribution distribution. Another example with NBC Sport, very simple. I mentioned the return feeds. That's basically you have a talent, you're doing an interview, it moves, it goes to the NBC Sports group, like in their headquarters, and at the same time you send that same feedback as it gets there with some instructions so that the talent can see what they're doing. So you can contrast the previous complex setup to this, very simple setup. They're serving the same purpose. Another one that I really like, I just picked a few here and there, is what Sky News did. It's very ingenious. They implemented SRT, they put it on a 35-pound Raspberry Pi, that can handle, like it has an H.264 encoder. So they integrated the SRT package straight from the GitHub on that. They're leveraging the simple encoder in there, and they're just doing field reporting and global delivery extremely cheap, extremely effective. And it's really a testament to what I mentioned earlier on in the early of the talk is really the resource utilization and the footprint of the protocol is very, very minimal. So it's designed to run on very underpowered embedded devices. And that's exactly what Sky tried to do. And they're running their on the cheap field reporting and global delivery with that. So again, something to kind of mention about that here. Microsoft, the SRT was leveraged, for streaming to multi-site events around the globe. So in this case, you had an event, for example, and you have the main stage. That main stage is sending the signals. Of course, you're recording it on that main stage, obviously, just to maintain redundancy. SRT is leveraged so that you can send the signal across that venue to what they call the overflow rooms. So you have the keynote, right? And then you have the overflow rooms. It's still over the LAN, but still even the LAN, believe it or not, in these convention centers, usually they move these signals over fiber. So SRT replaced the fiber. It used the current infrastructure of the event and was able to send it to all the overflow rooms, making sure that the signal gets there. Of course, sometimes you also have remote locations. So let's say you have the convention center and 2 hotels. So the same signal goes also to those remote locations. And then it gets reflected to the cloud where it gets processed in Azure and then sent to the internet viewers. So again, another real-life scenario of how SRT is used in this case. You can see how different people use it in different ways. It's always focused on the contribution distribution. Al Jazeera, that's their newsroom in the cloud. Basically, you get from the original GS, you send it over SRT. Make TV is actually they're showing their stuff here. It's basically allow the producer to select which feed it needs to send and gets produced at the end of the side here. So you receive it from the location. This happens to be the UN. In New York, you receive it over SRT. It gets selected by the producer, like a switchboard with Make TV, gets passed to be packaged in MXF and then dumped into the Avid Media Central, and then the editors picks it up, starts cutting, and then producing highlights or whatever out of that event that is happening in the UN. So again, another real-life scenario of how SRT is being leveraged, in this case for a broadcast cloud workflow. MediaCon, very similar workflow where they have basically they're moving it from on-prem to the cloud. So this is basically the contribution side, and they have SRT, and this is all, it's integrated on their own equipment. They're sending kind of double protection, SRT and the VPN, and then they're getting it to the data center for displays. Same thing for distribution over the cloud. And I think that's about it. I would like to, try to, there's a lot of work with SRT, so this is more of a call of action, how you can engage with the growth and the community. We had a Blockfest. We're going to have another Blockfest. The one in May, there was 57 people participating in it to test the interoperability. We're planning another one in November or December, putting together an advisory board so that we can help in the direction of SRT and what we need to do next or whatever. And if you go to the SRT Alliance, you can see if you can participate in some of those. SRT has been integrated in very successful open source projects. So GStreamer has a native integration with it, which is very important. If you have embedded devices, and leveraging the GStreamer framework, multimedia framework, then you'll have an immediate integration with SRT. FFmpeg, for applications, server-based, application-based, cloud-based, or whatever. So you have native integration within FFmpeg. So the barrier of entry to adopt and use SRT is very low given GStreamer and the FFmpeg. Of course, if you want to play it back, you have native support of it in VLC. Wireshark, if you want to analyze the stream and what's happening, we used to have a plugin for Wireshark. Last week, actually, it was the submission for SRT native support in Wireshark, not as a plugin, but in their main branch, happened last week, and it's going to be released. So this way you can analyze your signal. And of course, the BA, which offer another framework. As I mentioned at the beginning of my talk, we're like 170 and growing to date. There's a lot of marquee names. Very happy about the adoption, trying to get everybody to work together. And really, that's my call to action, if anything, to take away from this presentation is we're always going to be better together. There are challenges that we need to solve. We need to maintain interoperability between people. Haivision produce their own encoders. There's many encoder companies and decoder companies leveraging the SRT. That's fine. At the end of the day, it's servicing the end consumer where my gear is compatible with my competitor because I'm not the only one producing encoders or transcoders. So maintaining interoperability between different vendors is very important. Having a standard where you can have a feedback and see how you can move it forward and really steer that direction. So I really encourage you to participate. Either go to GitHub and download the code or play with it or send requests or complaints or whatever. You can go to the SRT Alliance to see who's there, see how you can get engaged more. We have a Slack channel, and as mentioned, that we have virtual Blockfest that helps us engage. And I'm exactly 5 o'clock, so it's great. Thank you very much for all your attention. I apologize for the technical malfunctioning, and I appreciate you coming. Now you can enjoy your beer and the happy hour. Thank you. I'm open for a question, guys, if you want. And just one warning, though. I have 55% hearing loss. So even with my very, very expensive hearing aid, it's still sometimes hard for me to kind of really disperse and understand the words. So please bear with me.
Do you have any real-life data about how much packet loss can be recovered safely?
Very good question. We've tested this up to 20-25% packet loss, and we were able to recover. Now, that's really not a real-life scenario, but under our stress testing, that's what we have. The typical loss is around 2 to 3%. If you have 20% packet loss, then you should change your network, but yes. Yeah, but that's where we tested it for, stress testing it for. A lot simpler and easier to start with. That's, from a development point of view. WebRTC is fantastic, but it had compounded implementation complexities that made it a little bit difficult. Also, I don't think it's suited for high-quality broadcast workflows. I think it handles better lower bitrate streams. It has some issues in scalability, but hey, I can't say anything against it, right? I mean, it's there. It has its niceties. The best thing about WebRTC is you can receive it natively in a browser. That's the best thing. And actually, we're doing some real work right now so that you can receive SRT native into the browser using some UDP back channels. So once I get that and get SRT native into the browser without any plugins, then that advantage of WebRTC becomes minimal. But again, I mean, as I mentioned in the early, it provides an alternative. I don't try to pretend that I'm replacing WebRTC, right? It's good for what it needs to. In our industry, our judgment was, and that's the bulk of the industry, no one is using WebRTC to have, live event contribution to the cloud. You don't use that. You use WebRTC to receive it in your browser or for like conferences, right?
Just curious, you said that people were using SRT for just audio. Do you have like an example of a case of someone using SRT for just audio?
Yeah, and actually internet radio, hey. Stream guys are actually using it heavily for internet delivery of internet radio. So they have, I don't know, they support 10, 12, whatever, internet radio stations, and they send that over SRT. Yeah.
In one slide there, where you were showing Microsoft, were those multiple locations that had speakers? Because we were looking for.
The Microsoft, you said?
Yeah.
Okay.
Microsoft conference, I think. I thought I saw two cameras. I thought I saw a camera in each of those boxes
Yeah.
on the left. So those are speakers at both locations. How many locations can you have? Because we have a use case where we may need 3 executives speaking real time, 3 separate locations over our internal network.
Mm-hmm.
Over wide area circuits, but would that be a solution for that?
Absolutely. I mean, especially also for the bidirectionality. I have to say that it's not a way that everybody is using it, but it's definitely geared for that. It has a very, very low latency. It's very suited for interactive applications, and being able to be directional, then you can definitely have a conversation if need be. So.
We're using it today, and it works great.
Oh, yeah?
For field offices where we have our president speak, sometimes at remote locations, like even at a conference, the only thing it's not a challenge. The only thing we have to do is get that MAC address or the IP address of that, where they are in that hotel, and relay that back so they get to work wonderful.
It works. I mean, the example you're giving is very important because the barrier of entry is low. I mean, we have another example from Azure. They handle also most of the traffic for the NFL network. Basically, their challenge is they have these analysts in different locations. Most of them are in their apartments or whatever. They used to leverage MPLS. But then for MPLS, you need, it's like you need 3 months to get it installed and all that, and then you need to be committed to it for 3 years. You're in your apartment, so they switch completely to SRT. They have the encoders with the talent, and they have SRT, and they do all their remote interviews to the analyst over SRT, and that's for all of the NFL network. I don't mean NFL Network, i.e. the game or whatever. NFL Network basically handles behind the scene, the training camps, the interviews or whatnot. That's what happens. Great. Thank you very much again. Please enjoy the beer. I appreciate you coming.